Today, we shall be looking at how to find the domain of a function. The domain of a function is defined as the set of input values for which the function f of x produces an output. In other words, we are saying that the domain of a function is the set or the full set of x values that can be plugged into a function. What are we really saying? Let's consider this function y equal to 2x and this other function here y equal to 1 over x. Let us see if we can understand what the concept of domain is. Consider this set x, which we call the domain, and this other set here y, which we call the codomain. So for the first function here, y equal to f of x, so our f of x is 2x. In this case, our f of x is 1 over x. If in the domain we have the following elements, 1 or 0, 1 and 2, let's see what happens to this function. If we plug in 0 into this function, what will be the image? So 0, so we have 2 times 0 is 0. So 0 will be mapped to 0. If we plug in the value 1 into this function, what do we have? We have 2 times 1 is 2. So 1 is mapped to 2. If you put in the value 2 into this function, what happens? We have 4. So 2 is mapped to 4. So the elements 0, 1, and 2 are called the domain of the function y equal to 2x. The question we want to ask is this: is it possible that there are other values that can be plugged into this function to get images? The answer is yes, there are. For example, we can plug in 3 into this function, and 3 will give us what? And 3 will be mapped to 6. We can plug in 4 into this function, and 4 will be mapped to what? To 8. We can plug in 5 into this function, and 5 will be mapped to what? We map to 10 in the codomain. The question is, now, can we list all the members of the domain? The answer is no. So here we want to find out, we want to get techniques that helps us list the elements of this domain. Now let's go to this other function. If you plug in the value 1 into this function, 1 will be mapped to what? 1 will be mapped to 1 in this function. If you plug in the value 2 into this function, 2 will be mapped to what? 1 over 2 will be mapped to 1 over 2. If you plug in the value 3 into this function, and 3 will be mapped to what? 1 over 3. What happens if you plug in the value 0 into this function? We get the number 1 over 0. And as you well know, in mathematics, 1 over 0 is not what? Is not defined. 1 over 0 is not defined. What does this mean in essence? This means that even though 0 had an image in the first function, in the second function, 0 has no image. This tells us further that certain values which are in the domain of some functions are not in the domain of what? Of other functions. Therefore, the type of function we have will determine the best method for finding the domain of the function. So we shall proceed to look at one or two types of functions and see how we can find their domains. The first type of function we shall look at are polynomial function. So we say domain of polynomial functions. Now, you should know what polynomials are, I guess. So polynomials are simply, let's say f of x is equal to anx to the power n plus anx n minus 1 plus it goes on and on plus a1x plus a0. So in a nutshell, A polynomial is just a function that has, either ascending or descending powers of x. For example, say 2x squared, that is f of x, equal to 2x squared plus 3x plus 1. Here, the powers of x are descending. We have 2 here, we have 1, and we have 0. So this is what they call a polynomial function. Okay? And of course, this is what we call a quadratic polynomial function. We could have cubic, for example, negative 6x cubed, say minus 6x squared plus 4. And this is also what a polynomial function. Now, how then do we find the domain of such a function? That is to say, how do we know the kind of numbers, or how do we know what kind of numbers that when plugged into this function, we have, unique images? Now, we said the domain d of f, which are denote domain of function with the letter d of f. Now, for polynomial functions, we said the domain of all polynomial functions is equal to what? The set of what? All real numbers. And that set is denoted as what? With what? Letter r. So we say that the domain of all polynomial functions is the set of all real numbers. What does this really mean? Let's consider an example. Say y, or say f of x equal to, say, 2x. This is a polynomial function where the highest power of x here is 1. So we would call this a polynomial function of degree 1. Question is, what is the domain of this function? And we are saying here that since this function is a polynomial function, its domain is nothing but what? R, the set of all real numbers. What does this really imply? This implies that in the set of real numbers, if you plug in any real number into this function, we are bound to have an image for such a real number. So if, for example, if you plug in 0 here, the image will be what? 2 times 0 is what? Is 0. If you plug in 1 here, you get the image 2. If you plug in negative 1, you get the image negative 2, and so on and so forth. We are saying that there is no value in R, there is no number, there is no real number, such that when plugged into this function, that it fails to give another real number. So we say that the domain of all polynomial functions is nothing but what? R, the set of all real numbers. So if you have another polynomial function, y equals to, say, 3x squared minus 6x, say, plus 10, and you're asked again to state what the domain of y is, or of f, because f of x is 3x squared minus 6x plus 10. What do you observe again? The function f of x given to us here, 3x squared minus 6x plus 10, is again a polynomial function. And since a polynomial function, you say the domain of the function is what? Is the set R, which is set of all real numbers. The next kind of function we want to consider is the domain of a function with a fraction. Domain of a function with a fraction. So we are looking at functions of the type, say, p of x over q of x. So f of x is a function that is a fraction. And of course, we call such functions in mathematics rational functions. We call them what? Rational functions. So we are looking at domain of functions that are rational. Now, to find the domain of a rational function, we have to be very careful. We say set the denominator equal to 0 for fractions with a variable in the denominator. Now, what we are trying to say here is this. If the function you have at hand is a fraction of this form, p of x over q of x, there is at least one point that is not in the domain of this function. And to get that point, there could be more points, depends on how the function is constructed. There is at least one point that is not in the domain of this function. Now, to get that point, or points, as the case may be, that are not in the domain of the function, you simply set the denominator, in this case, q of x, to 0. And we solve the resulting equation to get the value of x. Now, when we do this, the value of x we obtain here becomes the value of x that will not be in the domain of the function. So in that case, we would say that the domain of the function is still the set of all real numbers except at the point where q of x is equal to 0. We shall illustrate this with two examples. First, say f of x is equal to the function 1 over x, a very simple function, 1 over x. The question again is, what is the domain of this function? And what does this mean? What are the values that can be plugged into this function that will yield images? Question is, does it mean further? If I plug in 1, will I have an image? If I plug in 2, will there be an image? Is there one or two? Are there one or two numbers rather that when plugged into the function, they will have no images? What do you observe? The function 1 over x is a fraction. And of course, in the denominator, there's a variable x. You watch out for that. There's a variable x. Of course, if there's no variable x, then the function is just a constant function. Okay, good. Now, since we have x in the denominator, we are saying that to find the domain of such a fraction, we set the denominator. So we say we set the denominator x to what? To 0. And solve. And in this case, x is just equal to what? 0. So what does this mean? This tells us that the domain of the function given to us is a set of all real numbers. Of all real numbers except the point, except what? Except what? 0. Except 0. Why are we saying except 0? Let us see. If we plug in the value 0 into this function, what do we get? We get f of 0 equal to 1 over 0. And again, in mathematics, division over 0 is once again undefined. So we are saying now that in the set of all real numbers, this is the only real number that does not produce a unique image in the function f of x equal to 1 over x. So the domain of the function here is a set of all real numbers except 0. The second function we'd like to consider is the following. F of x equal to 2x over x squared minus 4. The question again is to find the domain of the function f. We observe again that this function is a fraction with a variable x in the denominator. And the rule says that if we have such a function, we should set the denominator x squared minus 4 to equal to what? Equal to 0 and solve. So if we set these two and solve, what do we get? We get x squared is equal to, this negative 4 to the right becomes plus 4, and then x is equal to the square root of 4, and then what is x? And this is nothing but what? Plus or minus what? 2. Plus or minus 2. And what does this mean? This means minus 2 and what? And plus 2. So we now say that the domain of the function f is what? The set of all real numbers except what? Except negative 2 and positive what? 2. So what we are saying here again is that for the function f of x equal to 2x or divided by x squared minus 4, all real numbers when plugged into this function will give us images except the points negative 2 and plus 2. How? If we plug in negative 2 into this function, at the denominator, we are going to be having negative 2 squared is 4. 4 minus 4 is 0. And again, division over 0, we said is undefined. If we plug in the value 2 also into this function, we get 2 squared minus 4, which is also 0. And we'll be having division over 0, which is again undefined. We observe here, we must make this remark, that for a fraction, for a function as a fraction, we place emphasis on what happens at the denominator and not really at the numerator. The last thing we're going to look at today is domain of a function with square root. Domain of a function with square root. Now, if we have such a function, we say that, okay, to find the domain, we said you set the terms inside the radicand to be greater than or equal to 0. Set the terms inside the radicand to be greater than or equal to 0. And what's the radicand? Radicand simply means the square root sign. So whatever it is we have here, whatever values you have there, you set them to be greater than or equal to 0. Now the question is, why do we really do this? If we have, for example, the square root of -4, what would this value be? If you're familiar with complex numbers, the square root of -4 will be what? 2i. Will be the value 2i. Of course, where your I is nothing but what? The square root of -1. But what do we observe? We observe that when we have a negative number inside our radicand, the value of the value that comes out is 2i. And 2i here, this value 2i is not a real number. But we had defined in our previous class that the functions we are dealing with in this series of lectures are real valued functions. That is to say, there are functions that when we plug in real numbers, we get back real numbers. But we observe here that if we have a radicand and the value of our radicand and the value inside the radicand is negative, the value that comes out becomes a complex number and not a real number. So, to guarantee that we always have a real number when we plug in some values into the radicand, we now say, okay, we have to set everything we have inside the radicand to be greater than or equal to 0. Why? Because 1, if what we have in the radicand is 0, then the square root of 0 is nothing but what? 0. And 0 is a real number. If what we have inside the radicand is greater than 0, then of course we are also guaranteed that that number is a real number. Let us discuss this further with an example. Say we have the following function: f of x is equal to the square root of x minus 4. The square root of x minus 4. The question is, you find the domain of the function f. What do we observe? We must first look at the type of function, in question. And we call this kind of function, we call algebraic function. We call them algebraic functions. Algebraic functions. You see, the function inside x minus 4 is a polynomial function, but it has a square root. So it now becomes an algebraic function. So to find the domain of this function, we observe that, okay, there's a radicand. So the value inside of it, which is x minus 4, we say x minus 4. So we set x minus 4 to be greater than or equal to 0. This is what we must do. This is the only way we are guaranteed that what we have inside the radicand are real numbers. So we now solve this inequality. So we have here x is greater than or equal to what? Greater than or equal to 4. And what does this mean? This means that if we sketch our real line here, we have 0 here, we have 1, 2, 3, 4, 5, and so on. We say x is greater than or equal to 4. We are here, this is 4, greater than or equal to 4, greater than, that is to the right of 4. What this implies is that the domain of this function are values from 4 to plus infinity. So we'll write that as the values from 4 to infinity and close. And this becomes the domain of the function f. Why is this true? Let us see. Why do we think, or why do we say that the values behind 4 to the left are not in the domain of f. If we pick the value 3, for example, and plug into the function f, let us see what image that produces. So we have f of 3. So f of 3 here, by putting 3 here, is equal to the square root of 3 minus 4, since x is now 3. And this gives us the square root of 3 minus 4 is negative 1. And the square root of negative 1 is nothing but what? I. And I is not a real number. The same thing will happen if you put the value 2. Same will happen if you put the value 1 and every other number to the left of the number line. But if we plug in the value 4 into this function, what do we get? We get f of 4 equal to the square root of 4 minus 4. And 4 minus 4 is 0. And the square root of 0 is 0. And 0 again now is a real number. If you plug in the value 5 into the function, we get the square root of what? Of 1. And the square root of 1 is nothing but 1, which is also a real number. Whatever value we plug in into this function, from 4 to wherever it is at infinity, wherever it is, up to 100, 1 million, we are guaranteed that the value of the image of this function will be a real number. So we say that the domain of this kind of function is what? Is the closed interval, left closed interval 4. Why do we close at 4? Because we said x is greater than or equal to. So that means 4 is inclusive toward infinity. We put this, the interval is open at infinity because infinity is not a number that we know. So the domain of this function is 4, infinity. And for all functions with square roots, this is how we determine the domain for such functions. So we say, remark here is you cannot take square roots of a negative number.